In this video, we will explore one of the boosting models, the XGBoost model, and implement it through coding. For your reference, the XGBoost model operates on the same principles as the gradient boosting machine model, so watching the previous video on gradient boosting machine might help you understand it better. The XGBoost model stands for Extreme Gradient Boost. It is a versatile algorithm applicable to both classification and regression tasks, enhancing the traditional gradient boosting algorithm. XGBoost fundamentally follows the concept of the vanilla gradient boosting machine, calculating residuals and minimizing them to build the optimal model. However, XGBoost offers several additional features, such as regularization, approximate algorithms, and parallel learning, which provide high performance and efficiency. An important feature of the XGBoost model is its objective function, which combines the loss function and regularization. This objective function is minimized during optimization. Specifically, the objective function is the sum of the loss function and regularization. For regression tasks, the loss function typically measures the difference between the actual values and the predicted values. For classification tasks, the loss function usually involves cross-entropy or similar measures. Regularization in this context helps control the complexity of the model, preventing overfitting. This can be expressed through mathematical formulas. Let's first take a brief look at regularization. Imagine we are using a decision tree model to classify red and green items. Which of the two models do you think does a better job of classifying red and green items? The model on the left overfits, meaning it classifies the training data perfectly but fails to generalize well. On the other hand, the model on the right does a reasonably good job of classifying red and green items. As the decision tree becomes more complex with more leaves, it can perfectly classify the training data but may suffer from overfitting, leading to poor performance on new data. Therefore, if we can control the complexity of the model, we can mitigate the overfitting problem to some extent, and regularization helps us control the complexity of the model. Let's take a closer look at the regularization formula shown in the previous slide. In this formula, the letter T represents the number of leaves in the decision tree, and omega represents the weight of each leaf. Imagine we have 5 people labeled A, B, C, D, and E. Using a decision tree model, we classify them into 3 groups based on age and gender. Group 1 with A, Group 2 with B, and Group 3 with C, D, and E. The number of leaves is 3, and we assign weights of 2, 0.1, and 1 to these groups, respectively. When we plug these values into the regularization term, it can be calculated as shown. Gamma controls the influence of T, the number of leaves. Essentially, gamma affects the additional splitting of leaf nodes in the tree. A higher gamma value results in a more conservative tree with fewer splits, leading to a simpler tree structure. Conversely, a lower gamma value allows for more aggressive splitting, leading to more complex trees. Next, let's discuss the lambda parameter in the XGBoost regularization formula. In XGBoost, lambda represents L2 regularization. When the lambda value increases, the weights decrease. Conversely, when the lambda value decreases, the weights increase. Therefore, a higher lambda value results in stronger regularization, reducing the weights. On the other hand, a lower lambda value results in weaker regularization, allowing the weights to remain higher. This means the model is permitted to fit the training data more closely. Let's explore the advantages of the XGBoost model. If there are a total of 40 data points and we evaluate all possible split points, we would need to evaluate a total of 39 splits. This process, where we evaluate all possible splits and choose the best one, is known as the greedy algorithm. As the term greedy suggests, this approach exhaustively evaluates all possible splits. At each step of building the decision tree, the algorithm evaluates all possible splits for each feature, with the hope of finding a global optimum. This selection is made without considering future implications or the overall structure of the tree. This greedy algorithm is the method used in vanilla GBM. However, if we divide the 40 data points into 10 groups, we end up with 4 data points per group. and each group would have 3 possible splits. Therefore, if we evaluate 3 splits for each of the 10 groups, we need a total of 30 operations. In contrast, as explained earlier, the greedy algorithm would require 39 operations, but in this case, only 30 operations are needed, making it more efficient. This method is known as the approximate greedy algorithm. When there are a number of observations, the data can be divided into smaller segments instead of individually testing every possible threshold. This allows XGBoost to quickly identify candidate split points without evaluating every possible value. Now let's discuss another advantage of the XGBoost model: parallel learning. While traditional vanilla GBM builds one tree at a time, sequentially based on the errors of the previous tree, XGBoost processes the tree construction by finding the optimal split points in parallel. This means that each split operation is independent of others, and the results are integrated into the overall model training. Thanks to this approach, XGBoost can train much faster, especially on large datasets. This slide displays the screen for coding the XGBoost model. You can find the Jupyter Notebook file on GitHub, where you can download it and execute it directly. Similar to previous AI models, we first import necessary libraries such as NumPy, Pandas, and the train test split library. Then, we load the Excel dataset. After assigning X and Y variables, we split the dataset into training and testing data, typically using an 80 and 20 ratio. To build an XGBoost model, you first load the XGB library. After loading the library, you convert the data into a D-matrix structure for efficient data processing and training with the XGBoost model. Then, you put various hyperparameters into a variable called params. Here, softmax is used for multi-class classification, and since the iris data consists of 3 classes, it is defined as 3. Additionally, ETA refers to the learning rate, and lambda and gamma are regularization hyperparameters. After defining the parameters, you train the model with the training data. As a result, the model achieves 100% accuracy on the training data and 96.7% accuracy on the testing data. You can create a simple code using the for command to check whether the actual and predicted species match. As shown in this slide, if they match, it will display true. If they don't, it will display false. Additionally, you can use the plot importance command to visualize the importance of the features. The F-score on the x-axis indicates the frequency a particular feature was used as a split criterion in the tree. A higher value means the feature has a greater impact on the model's predictions. Therefore, it shows that the width of the petal has the greatest impact on classifying the iris species.